To understand the behavior of elements across the periodic table, we start with a single measurement, the force the nucleus exerts on its outer electrons. This is effective nuclear charge. While the nucleus pulls inward, the inner shells of electrons provide a physical barrier. They repel the outer valence shell, shielding it from the full positive charge of the center. This is the screening effect. Moving from left to right across a period, we add protons to the nucleus without adding new inner shells for shielding. The inward pull, the effective nuclear charge, grows stronger, and the atom physically shrinks. This inward pull establishes the baseline for how elements react and bond. However, specific physical conditions can override this trend, creating discrepancies that often appear on exams. This question asks for the correct order of ionization potential, the energy needed to remove an electron, for carbon, nitrogen, oxygen, and fluorine. While the general trend suggests a steady increase from left to right, the measured data shows a specific deviation. Nitrogen actually has a higher ionization energy than oxygen. In its ground state, nitrogen has a 3-electron p orbital. This half-filled configuration is highly stable. Removing an electron requires enough energy to break that symmetrical arrangement, which outweighs the standard trend. This conflict between trends and physical reality appears again in electron affinity. Based on atomic size alone, fluorine should release the most energy when accepting an electron. Instead, the highest value belongs to chlorine. Because fluorine is in the second period, its valence shell is physically small and densely packed. An incoming electron faces intense repulsion from the electrons already there. Chlorine, in the third period, has a larger volume that can more easily accommodate the additional charge. The text in this section confirms that the second period has lower values than the third because of this repulsion, making chlorine the element with the highest electron affinity. In these cases, the specific stability of an orbital, or the physical constraints of space, override the raw pulling power of the nucleus. These same physical principles govern molecular bonding. While 3D sketches are helpful for visualization, there is a more efficient way to determine the hybridization of a central atom during a timed test. The steric number formula provides a direct path to geometry. By calculating this value, you identify the hybridization state. V is the central atom's valence electrons, M is attached monovalent atoms, like hydrogen or halogens, and Q is the net charge. For phosphorus pentachloride, we add 5 valence electrons and 5 monovalent chlorines. Half of 10 gives a steric number of 5, an sp3d hybridization. Practice with xenon tetrafluoride. Xenon has 8 valence electrons plus 4 monovalent fluorines. Half of 12 is 6, an sp3d2 hybridization. This calculation bypasses the need for manual structural drawings, providing the same result through simple arithmetic. We can use a similar numerical shortcut for molecular orbital theory. Calculating the bond order for diatomic molecules like O2 or its ions usually requires a full energy diagram, but there is a faster method. Every system with 14 total electrons has a bond order of 3.0. For every electron you add or remove from that 14-electron baseline, the bond order drops by exactly 0.5. Table 2.3 shows this relationship in practice. Nitrogen, with 14 electrons, has a bond order of 3. Oxygen, with 16 electrons, is 2 steps away from the baseline, resulting in a bond order of 2. This master sheet consolidates these trends and shortcuts. It anchors the baseline force of the nucleus, highlights the specific structural exceptions, and provides the formulas for hybridization. Mastery of these concepts comes from integrating the baseline force of the nucleus with the specific physical limits of orbital geometry and electronic repulsion.